At 0 degrees Fahrenheit, a thin-walled shelter can lose warmth so fast that your body's heat barely makes a dent. Hypothermia sets in once your core temperature falls below 95 degrees Fahrenheit, and frostbite may strike in only 30 minutes. Yet countless people manage to heat shelters without gas or electricity and survive freezing nights in vehicles, tents, and improvised cabins. What physical laws and survival strategies make this possible? And why is simply staying inside not enough to prevent life-threatening cold? Inside a winter shelter, heat slips away through 4 main routes. Conduction is the first. When skin or clothing touches cold surfaces, plywood, metal, or frozen ground, heat drains from the body into those materials. Even a 5-millimeter plywood wall, barely thicker than a pencil, can leak nearly 2,000 watts if it stands between warmth and deep cold. That is more than a human body can ever replace. Convection follows. Moving air, whether from a stiff wind outside or a draft sneaking through a seam, pulls heat away from walls and bodies. On a calm night, convection is slow, but add wind and the effect multiplies. A strong breeze can drive heat loss up to 1,600 watts, as air whisks warmth away much faster than stillness ever could. Radiation is quieter, but relentless. Every object emits energy as invisible infrared waves. In a winter shelter, heat radiates from people and surfaces toward anything colder, especially the open sky. Even if the air is still and there is no contact, 400 to 600 watts can vanish this way, shaped by the temperature gap and how surfaces reflect or absorb energy. Evaporation is the final thief. Each breath releases water vapor, and even mild sweating adds more. As moisture leaves skin or dries from clothing, it carries heat, about 20 to 30 watts per person at rest, more with movement. Wet gear or condensation only increases the toll. These 4 forces, conduction, convection, radiation, and evaporation, work together, explaining why thin shelters bleed warmth and why each pathway demands its own defense. A resting human produces between 70 and 100 watts of heat, about the same as a small incandescent light bulb. This figure, confirmed by USARIEM physiology research, sets a hard upper limit on what the body can contribute to warming a shelter. In a freezing environment, losses from conduction, convection, radiation, and evaporation add up quickly. For a thin-walled structure exposed to deep cold and wind, the total heat lost can reach several thousand watts, far more than a person's metabolism can replace. Even with 2 or 3 people inside, the combined heat output remains a fraction of what leaks out unless something changes. This gap between what the body can supply and what the shelter loses is the core challenge of heating a shelter without gas. The numbers are stark. A single person at rest, generating maybe 80 watts, faces losses from bare plywood walls or drafts driven by wind that can exceed 3 or 4 kilowatts. That is a deficit of more than 30 to 1. No amount of huddling or layering alone can close that gap when the structure itself is bleeding energy into the environment. This is why every passive measure, including insulation, ground barriers, and draft control, must work together to shrink the losses down to the scale of what the human body can provide. The science is clear. Survival in cold weather shelters depends not on producing more heat, but on slowing the escape of what little is available. Without major reductions in heat loss, even the best off-grid heating ideas fall short. The next step is to look at how people actually bridge this gap, using materials and designs that cut losses by 90% or more. Insulation is the first and most effective tool for shrinking the gap between body heat and the winter cold. The science behind it is simple. Still air is one of nature's best barriers against heat loss. A single, sealed air gap about an inch thick delivers an R value of roughly 1.0. That's the same principle behind double-pane windows or the lining in a good parka. Foam boards, especially extruded polystyrene, XPS, take this further. With an R value of 4 to 5 per inch, a 1-inch XPS sheet cuts conductive heat loss by a factor of 30 compared to bare plywood. Polyisocyanurate panels, often faced with foil, raise the bar even higher, combining low thermal conductivity with a built-in radiant barrier. Wool is another option, offering R values around 3.5 to 3.8 per inch. Unlike synthetics, wool keeps its insulating power even when damp, helping buffer against condensation and sweat. For radiant heat loss, reflective layers like mylar are key. These thin metallized films reflect up to 97% of infrared radiation when paired with an adjacent air gap. In practice, a mylar sheet sandwiched between foam boards can bring the total assembly to an effective R value of 5, slashing both conduction and radiation losses. As one product engineer from a leading outdoor gear company puts it, every layer that traps still air or reflects heat is another hour of safety when the temperature drops. The numbers back this up. Layered insulation can reduce total heat loss by over 90%, bringing the demands on body heat into reach. This is the foundation of insulation winter strategies, turning thin-walled shelters into survivable spaces, even when off-grid heating is not an option. Beneath every winter shelter lies the largest single pathway for heat to escape: the ground itself. Unlike walls or roofs, the floor sits in direct contact with frozen earth or snow, which acts as a bottomless reservoir for stealing warmth. Field data from the Cold Regions Research and Engineering Laboratory reveals that up to 40% of total heat loss in small shelters can occur through the floor. This dominance is not just theoretical. When researchers added a single 1-inch thick, closed-cell foam pad beneath a 2x2 meters bivouac at minus 15 degrees Celsius, the inside air temperature rose by 8 degrees Celsius. No wall or roof upgrade comes close to this kind of gain for the same effort. The reason is simple physics. The ground's thermal conductivity is far higher than air, so heat flows out of the shelter through the floor at a rate that can quickly overwhelm what the human body can supply. Even the best sleeping bag or wall insulation does little if body heat is draining into the soil below. Foam pads, layered cardboard, or any material that traps still air beneath the occupant create a decisive barrier, cutting floor losses by more than 80%. For anyone relying on their own metabolic heat, insulating the floor is the most effective single action for heat shelter without gas. Without it, even the best insulated walls cannot prevent the relentless pull of cold from below. Drafts undermine even the best winter shelter. One loose seam can let cold air surge in, overwhelming what the human body can provide. Joe Listeburek stresses the importance of tight seals and controlled air flow, keeping insulation dry and effective. The recommended ventilation rate falls between 0.5 to 1 air change per hour, just enough to clear out moisture and carbon dioxide without letting warmth escape. With a convective heat transfer coefficient above 20 watts per square meter per degree, even a small draft can double or triple heat loss. The numbers are stark. A 24 square meter shelter can lose 380 watts through its envelope, while 2 people at rest produce only 150 watts combined. A 5-kilogram water bottle might delay the chill for half an hour, but not for long. Some try to fill the gap with candles or stoves, but the danger is real. Carbon monoxide becomes hazardous above 100 parts per million and fatal above 400 parts per million. NIOSH and CDC records show deaths every winter, often after vents clog or air stagnates. In a small, sealed space, a moment's lapse can turn warmth into a silent threat. Insulation and careful draft control remain the safest defense. Heat always moves from warm to cold, and the speed of that movement depends on how easily energy can cross the barrier between inside and out. This is the core law behind every winter shelter, whether it is a tent, a van, or a plywood hut. The goal is to lower the U value, the measure of how much heat escapes per square meter. For each degree of temperature difference, the lower the U value, the slower the heat loss. Insulation, ground barriers, and tight seams all work by reducing the rate at which energy flows out. Every improvement, whether foam, wool, or reflective film, shrinks the gap between body heat and the cold outside. Survival depends on matching the shelter's total heat loss to what the human body can supply, not on creating more heat. With every layer of insulation, each sealed seam, and a well-insulated floor, the numbers finally begin to align. Heat that once vanished through walls and ground now lingers inside. The draft that once pulled warmth away is slowed to a controlled trickle. The body's steady output, modest but constant, can finally keep pace with the environment's demands. Where once the deficit seemed impossible, the balance tips. Interior air holds above freezing, condensation is kept in check, and the shelter becomes a pocket of survivable warmth. What started as a losing battle against the cold is transformed, not by generating more heat, but by holding on to what little is already there. Every winter, thousands worldwide depend on insulation, not combustion, to keep shelters above freezing. As grid failures and extreme cold events rise, the science of heat loss and retention becomes essential for cold weather survival and hypothermia prevention. In the end, slowing heat loss is survival itself. Stay warm, stay informed.